In this lecture, we are going to learn concept of confounding and interaction in multiple linear regression. So outcome of interest is continuous variable. Before we specifically talk about linear regression, and let's use a motivating example to review what is the confounding. Okay, so first sessions we focus on confounding. And this is a paper examining effect of use of cardiac catheter among patients who have acute MI. This is a retrospective study using Medicare data, including 120,000 patients with acute MI of age 65 or greater. And the outcome is 1 and 4 year mortality, and we actually do look at 1 year mortality in today's lecture. Exposure of interest is use of catheter in 30 days from hospitalization for the index MI. And there are 65 potential confounders because this is the observation study, so we don't have a randomization to control for confounding. So we will talk about how we can control for confounding and in the data analysis stage. Okay. And this is the result of this study. Then of deaths among patients without catheter were 39%, and 1 year mortality among patients who received catheter, 14%. So if you directly compute ratio between these 2%, and that becomes 0.364, which is a relative ratio. So given this, and you may conclude there is 63% reduction in risk of death by using a catheter compared to not using catheter. And then can you finish your analysis? No. We need to look at whether we are comparing apple to apple. So let's see what we are comparing, what patient we are comparing. So this is the baseline characteristic table and showing data on the prognosis factors. So these are the factors which are thought to relate on mortality. And we want to make sure these factors are balanced between two groups. So let's say percent of patient whose age is less than 75 years old, it's 64% with catheter group, whereas 40% in non-catheter group. And there are 58% of men in catheter group and 50% men in non-catheter group. And 4.8% black in catheter group, 7.5% black in non-catheter group. And history of angina is 49.9% in catheter group and 44% in non-catheter group. And history of MI is 26% in catheter group and 33% in non-catheter group. And let's look at congestive heart failure, which is 10% in catheter group and 27% in non-catheter group. And percent of diabetes is 28.6% in catheter group and 37% in non-catheter group. Okay. And how about this one? Hospital characteristic. So this is the percent of patients who are hospitalized in the hospital whose annual AMI volume is greater than 200 patients. That's 30% for catheter group and 20% for non-catheter group. And given this, what do you think? Do you think we are comparing apples to apples? And probably no. It looks like catheter group contain the patient who have better prognosis, less number of congestive heart failure and a younger, for example. Okay. So if you ignore these imbalance on the prognosis factors and directly compare outcome percent of death between two groups, your analysis may confound. It's probably likely to confound, right? So what is your guess? Okay. So that is a point of next 10 minutes of discussion. Right? And these are the method of effective method to prevent confounding. Number 1, matching. Number 2, statistical adjustment. This use regression technique. such as linear regression and logistic regression. Number 3, stratification or restrictions. In stratification, and you divide your data to, for example, a patient with congestive heart failure, history of congestive heart failure, and without history of congestive heart failure, and analyze data separately. And number 4 is randomization. Okay, so we will talk about each item today. Let's start with matching. In matching method, among 73,000 patients who receive heart catheterization, and they look up each one of them, and then for each of the catheter patient, and then they match non-catheter patient whose background are similar. Backgrounds means data on each of these prognosis factors are similar. Okay, and then they repeat the process for entire 7,300 patients and who receive catheter. Okay? And then they end up having about 31,000 patients in each group. So this is one-to-one matching. So you have a same number of patients between the two groups. Okay? And you may be surprised knowing this analysis contains less than half of a patient in who receive catheter. And this means there are a large number of populations and they couldn't really find much patient without catheter and whose background is similar to a non-catheter patient. So those patients are excluded from the analysis. And now, after matching, and if you look at baseline variable, and you have baseline variables, they are actually very similarly distributed. So we have a good balance between two groups. And then among this matched cohort, if you compare 1 year mortality, which become 35% in non-catheter group and 19% in catheter group. So if you take a ratio, which is actually a little bit smaller with non-catheter and a little bit larger with catheter group. And then when you recompute relative risk, and now it's become 0.538. So there is 46% reduction in risk of death by using catheter. Okay, so this is a technique called matching. This presents a graphical representation of matching. So y-axis is outcome, and let's say some indicator for mortality. And x-axis is the severity of disease. And this n is patient without catheter, non-catheter. Disease patient with catheter. So the patient whose disease severity is very high and they are too sick to be operated. Therefore, they couldn't really find much non-catheter patient whose disease severities are similar. Okay? So these patients are excluded. And similarly for this patient, and their prognosis is much better. So everybody is getting operated. Therefore, can't find much with the patient without catheterization. So if you get rid of these two extreme populations, and difference and you observed in the analysis of matched cohort may be smaller than actual difference, including entire cohort. Okay? So this is very important to remember happening as a result of matching. And next one is statistical adjustment. So these people actually conducted two analyses, and one is a Cox regression without including any other covariate than who use catheter and non-catheter. That's the main exposure variable. And then also analysis of Cox regression including all 65 potential confounders. So they just stick in those covariates in the Cox regression model. Okay, so what this is doing is, this is doing actually very similar thing and you would do in your head without even using computer. So what would you do? So you know 39% of mortality in non-catheter and 14% of mortality in catheter can be compared directly because of a difference between difference in baseline prognosis, right? So no catheter group is much sicker. Okay? So therefore, in adjusted analysis, by using regression technique, we estimate how much sicker they are based on the fact they are sicker to begin with. Right? So what if they are not as sick? So in non-catheter group, and they actually discounted that excess mortality, and which they think is due to just a baseline imbalance. Okay, and by doing that, okay, so you would do this in your head, and I do same thing using computer, right? It's the same thing. And then if you compare the ratio mortality, and then the hazard ratio become 0.510, so the result becomes smaller. Okay, so this is a concept of statistical adjustment. We are not doing anything special. We are just using computer to do what you would do in your head very easily. Okay. So let's look at the definition of confounding. And confounding is a bias that results when a study factor effect is mixed with the effect of extraneous variable. What does this mean? Okay. And this means effective use of catheter is mixed with the fact non-catheter groups are sicker, and therefore, and that masks true association. So if we ignore those difference bias, okay, and result of study can be highly distorted. So when confounding occurs if a factor which is causally associated with outcome has an association with exposure of interest. Confounding occurs if a factor which is causally associated with outcome has an association with exposure of interest. And confounding is not a factor which is on a causal pathway between exposure and outcome of interest. So let me look at schematic presentations for this. Confounding occurs when a factor which is causally associated with the outcome happen to have association with exposure. Okay? An example, famous example of smoking and alcohol consumption onto the lung cancer. Okay, so we want to assess association between alcohol consumption to lung cancer. So that is our interest. And we know that smoking has a causal association to lung cancer. And then the smoking happen to have association with alcohol consumption because many smokers may drink and many drinkers may smoke. We don't know directionality, but we know there is association. Okay. So when the condition like this happen, then this factor can confound association between alcohol consumption to lung cancer. In next slide, I'm going to talk about relationship between statistical adjustment for confounding versus stratification. This is unstratified analysis. Unstratified analysis, I sometimes use the word unadjusted or crude analysis. And unstratified analysis is we analyze data using entire data set, so we don't split by subgroup. This graph is showing relationship between alcohol consumptions to lung cancer marker. Okay? And when you have data like this, and you may draw regression line like this, and you may conclude there is statistically significant association between alcohol consumption to lung cancer. Next data is actually the same as this data, but we separately plot smokers and non-smokers and look at effect of alcohol consumption on lung markers separately for smokers and non-smokers. And this type of analysis we call stratified analysis. Data are stratified by smoking status. And sometimes I call this as smoking specific analysis. Okay? And if you look at association of between alcohol consumption to lung cancer, and do you still think there is association? Probably not, because within the smokers, and slope is flat, so increasing alcohol consumption level does not really link into increasing lung cancer marker value. And same for non-smokers. So this is example smoking confounded association between alcohol consumption to lung cancer. So this is unadjusted analysis, unstratified analysis. You ignore effect of smoking. So we mistakenly said there is association between alcohol consumption and lung cancer. In this analysis, we adjusted confounding, or we controlled for confounding by subgroup analysis or by stratified analysis. So if we look at association within the smoker and non-smokers, there no longer is association. Okay? But let's look at this. If the results are the same, effective alcohol consumption is the same between smoker and non-smokers, and how about pulling these two results together? Okay. And especially if there is an effect of alcohol consumption, and then if we keep splitting data set, and analysis may suffer loss of power by small sample size. So when effect are relatively similar, and then you judge it's okay to take average. An effective way to combine stratified analysis is statistical adjustment. So not only including, so in addition of alcohol, you include a smoking effect in this regression. Okay, so this is the formula for linear regression. Okay. And this beta 1 is a correlation coefficient, is a regression coefficient for alcohol after you adjust for smoking. And this beta 1 is sample size weighted average of smoking specific effect of alcohol on lung cancer. Smoking specific effect of alcohol means these two slopes. Okay? So this beta 1 is smoking adjusted effect of alcohol on lung cancer, which is sample size weighted average between two smoking stratified effect or smoking specific effect of alcohol to lung cancer. And here's another example. And many people might think confounding, after you adjust for confounding, and we always lose the effect of exposure variable. And actually that depends on data sets. Let's look at this example. In this example, if you draw a line, and you can draw a regression line like this. And here you have much variations among data, so you may say even though slope seems positive, but it doesn't seem alcohol has statistically significant effect on lung cancer. But if we show data separately for smokers and non-smokers and assess the effect of alcohol separately for smokers and non-smokers, you actually do have a tight positive association between alcohol and lung cancer. And here, since stratified analysis suffer loss of power and the effect seems very similar between smoker and non-smokers, why don't we combine or pool the effect? So let's do adjusted analysis. So you simply include smoking in the equation. So beta 1 is now sample size weighted average of effective alcohol. And some of you may be wondering, what if the effect of alcohol seems different between smokers and non-smokers? Can we still take average? Okay. So if you think effect of alcohol is clearly different between smokers and non-smokers, and of course, we don't want to hide that difference. So analysis in this case, instead of pooling the effect, okay, by taking average, we will assess interaction. Interaction, another terminology, is effect modification. So here, clearly we can say effect of alcohol is modified by smoking status. So effect, when I say, what do you think if there is association between alcohol and lung cancer? Your answer is, well, it depends on whether you smoke or not. And that means effect modification, i.e. interaction. So interaction analysis, instead of just adjusting smoking in an equation, and you create the cross product term between smoking and alcohol, and then stick that terminology in the model. And if the p-value for this interaction term or cross product term is significant, then you detect difference in effect of alcohol between smokers and non-smokers. So key to differentiate if it's confounding or effect modification, i.e. interaction, is whether effect of your main exposure variable seems changing by the level of third factor. Okay? So in this case, if you judge these differences are meaningful, clinically meaningful, and then let's proceed your analysis assessing interaction. And if you think association seems similar between smokers and non-smokers, then you go ahead to adjust for effective smoking. Okay? All right. Right here, I'm showing you 5 different scenarios. Okay? For each scenario is showing association between alcohol and lung cancer, but separately for smokers and non-smokers. And for each scenario, I want you to identify whether smoking is either confounding or interaction, or neither confounding or interaction, and or if the main effect of smoking or if the main effect of alcohol. Okay, and this is not just a single answer, so you may choose multiple answers, multiple yeses. Okay, let's begin. So this scenario A, there is effect of alcohol both in smoking and non-smoking, and although there seems no effect of smoking, therefore these slopes overlap. Okay? And do you think smoking is confounding or there is interaction? And since two slopes seems the same, so you may judge there is no interaction. And how is it confounding? Do you think smoking confound effect of alcohol on lung cancer? And to judge if the factor smoking is confounding or not, what you do is you compare unadjusted analysis of alcohol versus smoking adjusted effect of alcohol. Right? So green is a crude, so unadjusted effect of alcohol. So this means you only look at these black dots and ignore red and blue, and you just put the straight line. What would be that line? That is a green. Okay. And then the orange is smoking adjusted effect of alcohol. So that you actually take a look at blue or red lines, and then you take average between these two. So since slope is the same, two slopes are the same, so since two slopes are the same, and smoking adjusted effect will look like this. And it's smoking adjusted slope and smoking unadjusted slope differ. It seems the same. Therefore, the answer is 3, neither confounding or interaction. And do you think there is a main effect of smoking? No, blue and red seems similar, okay, compared to this graph. It's much similar. And do you think there's a main effect of alcohol? Yes, slope is positive. It looks positive. So I judge I think there is association between alcohol and lung cancer. And how about scenario B? Do you think there is an interaction effect? Effect of alcohol seems the same between smokers and non-smokers. The effect of alcohol is quantified by the slope. Okay, so slope seems the same, and therefore I don't think there is interaction. And how about, do you think smoking is confounding effect of alcohol? And to judge that, and you compare unadjusted effect of alcohol versus adjusted effect of alcohol. So let's draw a straight line ignoring red and blue lines. Okay, so that's the unadjusted slope. And how about adjusted slope? Since two slopes are the same, so if you pull the two, it would be the same. So answer is number 3. Smoking is neither confounding or interactions for scenario B. And yes, there seems the main effect of smoking, because if you smokers and non-smokers, and value of lung cancer markers are a lot different. And yes, do you think there's a main effect of alcohol? Yes, because slope is positive. Okay? And how do you think scenario C? Scenario C, effect of alcohol quantified by the slope seems a lot different between smokers and non-smokers. So I do think there is interaction. And how about can smoking still confound the result? And let's examine. So ignore red and blue lines, and let's draw a straight line. That is this one. And then let's pull red and blue line and see what would happen if you adjust for smoking, and that would be this. And since slope of green and slope of orange seems different, so I judge smoking is confounding association between alcohol and lung cancer. So answer is 1 and 2. And do you think there is effect of smoking? Yes, because value seems larger. Value of lung cancer marker seems larger with smokers. Do you think there is main effect of alcohol? That I'm not sure, because if you go ahead to adjust, there may be effect shown by orange line, but it seems effect only happen in the non-smoker group, but not smokers group, smoking group. And scenario D, and how about this? And right, so do you think smoking is confounding association between alcohol and lung cancer? So let's draw an adjusted line, that is this. Okay, so you forget about blue and red, and you just put straight line over these black dots. Okay? And how about if you adjust effect of smoking, what happens? You take average between these two slopes, so adjusted slope would be flat. So since green and orange slopes are different, we judge smoking is confounding association between alcohol and lung cancer. So answer is 1. And how about interaction? Since slope seems the same, so I don't think there is interaction. Do you think there is a main effect of smoking? Yes, because value of lung cancer markers are much higher with smokers than non-smokers. Main effect of alcohol? No, these two lines are flat. So we don't think there is main effect of alcohol. If you look at unadjusted effect, and you might think there is association of alcohol, but this analysis is confounded by smokers, so we ignore. And how about scenario E? This is actually a very interesting scenario. Do you think there is interaction between alcohol and smoking? I.e., do you think effect of alcohol is modified by whether you smoke or not? Answer is no. Regardless of smokers and non-smokers, it seems there is a negative association between alcohol and lung cancer. Okay, so not for interaction. And how about, do you think smoking confound the effect of alcohol? Alright, so now let's draw crude analysis. Let's do crude analysis. Crude analysis, and you ignore red and blue, and you just put the straight line over this black dot, and that indicates positive association, right? But if you adjust for smoking, what happened? And you take average between red and blue, and since slopes are the same, so adjusted effect would be the same of red and blue. And do you think smoking is confounding association between alcohol and lung cancer? Clearly, yes. If you ignore smoking, you might see positive association, but if you adjust for smoking, you see negative association. So clearly there is interaction. So the answer to E is number 2, yes for interaction. And there seems main effect of smoking, and yes, there seems negative main effect of alcohol. So I hope this exercise help you to identify which is confounding, which is interaction. Using next 4 slides, let's review confounding in RCT. We use data from this study, a randomized trial of primary care-based disease management program to improve cardiovascular risk factors and glycated hemoglobin levels in patients with diabetes. So this is a 2-arm RCT among a patient with type 2 diabetes, and an intervention was given for 12 months, and we assessed hemoglobin HbA1c level at the end of the study. And this is the result of this study. So when we compare mean of 12-month HbA1c between intervention and control group, and the intervention group has lower HbA1c level by 0.81, and which was statistically significantly different. And we could publish the study with unadjusted analysis with direct comparison between 2 groups. And what many people actually do is go ahead to look at the balance and make sure if the randomization works or not. And what we did is, and we assessed statistical significance of each of these prognosis factors as causally associating to outcome variable of hemoglobin HbA1c, and between control and intervention group. Okay? And so we detected statistical significance with the age, and there is 3 years younger age with the intervention, and race, and there was p-value was observed as 0.1, and 70% African American was in intervention group and 59% in control group. And what many people do wrongly is, based on this baseline balance, they include age and race in the multivariable regression, and so that adjusted result is presented as a main result. And there is a fundamental problem using this approach. This is a larger baseline table we actually did publish in this paper. And what we really have to look in this baseline characteristic table is not the statistical significance of each variable on the list. And instead, we want to know directionality of imbalance seems happening randomly. Okay? So I highlighted the variables and where the imbalance happen in favor for intervention. For example, age. Intervention group's age was 3 years younger. Okay? And so I put the yellow. Okay, the younger people probably have a better prognosis. So I put the yellow here. And here, 70% of intervention group are African American compared to 59%. So this difference is happening in favor for control group, assuming African American is a risk factor for higher HbA1c. And similarly, and I judge numerically which one is higher and longer, and then I put the yellow and red. So if the randomization happened properly, and you should expect 50% of yellow. If you start seeing more yellows, and that may indicate randomization did not happen properly. Okay. So by looking at this, and I would say these two groups are pretty much balanced. In fact, very well balanced. And age may be statistically significantly different in favor for intervention, but there are the factors, and imbalanced directionalities go in favor to the control, so they cancel out. And what many people do wrongly is grab age and race, and include that in the multivariable regression, and then show adjusted effect as a main result. When the two groups have a good total balance, when you start adjusting for a particular variable, okay, and you start biasing a result. Beauty of randomization is when the randomization happens properly, it provides balance even among unmeasured factors. So why we even bother to check statistical significance for measured factor? And given that now many journals actually recommend not to compute statistical significance based on baseline characteristics for RCT. Let's review confounding in RCT. If the factor which is causally associating with outcome happen to have association with exposure, and it can cause confounding, okay, distorted result by confounder. And what the randomization does is cut association between exposure and these factors, prognosis factors, and by mechanism, okay, by cutting one of the conditions, and confounding cannot occur. Right? So two groups are pretty imbalanced. So therefore, we can directly compare effect of intervention on the outcome variable. So many RCT conduct unadjusted analysis. Confounding is more problematic in observational study where such randomization does not exist. So when you have data from observational study, and pretty much 100% of time you need to adjust confounders in analysis stage if it was not taken care in the design stage.